just start recording. So any positive charge is going to be repelled toward this negative charge. So the field lines point toward the negative charge, whereas our negative charges, well, they're repelled. Okay, so positive charges will have the field lines pushing away from them. Negative charges, we have the field lines pointing toward them. If we have, now some molecules and some objects have one side positively charged and one side negatively charged. We call this a dipole, an electric dipole. Electric because it has electric charge, dipole, di meaning two, pole talking about charges. So for instance, certain molecules are polar or have this dipole, and these tend to be things like water has a dipole, alcohol has a dipole moment, when it's polar, when it's non-polar, actually there. So there are a lot of different molecules that one side is positive, one side's negative, even though the total charge is zero. So that's the dipole. And it talks a lot about why different materials act the way that they do. Now, here is a representation of a water molecule. And water molecules is kind of a strange thing because it likes to freeze at a fairly high temperature, and it likes to also boil at a fairly high temperature. Now, if we compare it to other molecules, like methane is pretty close to the same molecular weight. Normally, when you get a heavier molecule, we get higher and higher boiling points, higher and higher melting points. But methane, which is CH3, it's a carbon, which is normally 12, and then it's got 4 hydrogen on the sides of it. It's actually shaped like a pyramid, but we're just going to represent it, in this sort of this flat world. So oxygen is 16 plus 2. It's about a molecular weight of 18. Carbon's 12 plus 4 gives you about 16. So they're about equal in mass. But methane, which is the main ingredient in natural gas at room temperature, is a gas. That's why we call it natural gas. However, water tends to be a liquid at room temperature. Why is that so? Well, that's because whereas methane is nonpolar, it has no positive and negative charges, the water tends to have a positive end. Actually, it has 2 positive ends, to be honest with you. And that's because the oxygen doesn't like to share its electrons. And here's the oxygen has a negative charge. So what happens here is that the water molecules will attract other water molecules, okay, and produce these weak bonds. We call these hydrogen bonds, which wouldn't have happened, if our water molecules weren't dipoles. Okay. Oops. All right. There are many ways to store electrical energy, okay? Probably the easiest way to store electrical energy is to create a battery, okay? A galvanic cell, a voltaic cell, if you will. And basically, what this battery does is it stores chemical energy that can be then released as electrical energy. But there's also a device that can't store very much energy, but it can quickly get rid of the energy, and it's used very commonly in electronics. We call it a capacitor. It has the capacity to store charge. Now, when we hook a capacitor up to a voltage source, okay, hook it up to a little voltage source, maybe like a little battery. That's a symbol for a battery. Okay, what happens is that we build up charge on different plates. People keep coming in and they keep distracting me. So if I connect a positive voltage to the plate on the left, I get lots of positive charges building up there because the electrons leave that plate, okay? So that gets positively charged. On the other end, on the plate on the right, I put negative charges on it. I put a negative voltage on it. So this will actually store charge. It will store energy where we can then connect it to something and get that flow of electricity back. So this is sort of like, filling up a bucket. You're filling up this capacitor with charge, okay? And then when you want to use this charge, you just connect it to something and empty that capacitor out. Now, what are some examples of where we need a capacitor? I'll skip some of this. Some of the applications where a capacitor is needed is, again, where we need a sudden amount of energy to power something very rapidly. Old flashes on cameras, now we use LEDs mostly, but old flashes on cameras, what they used to have were chemical batteries, okay? The batteries would sit right inside this little container right here. And these would obviously power the camera, but energy can only move from these batteries very slowly. The chemical reaction has to take place. So the energy that we get from this, well, it's not coming out of the battery very rapidly. And that's a problem because the flash, which is right here, okay, that little white thing right there, that flash, it needs a very high power, so lots of energy, but in a very short time. If I try to send electricity through this flash, okay, it won't light up. So what I do instead is I dump energy slowly onto this capacitor, and then it'll build up, build up, build up, just like that bucket is filling up. And then when I need all that charge and all that energy, I dump it within a millisecond onto the flash, and the flash, briefly lights up for a very short moment. So capacitors are very nice for a number of things. One, they're great for storing energy. The most powerful lasers that we have in the world actually use capacitors because, like the laser at Lawrence Livermore, it's called the National Ignition Facility, that uses more power in a microsecond than all the Earth. So to power that laser, you would need more than the energy than all the power plants on Earth could provide. So what they do is they charge up these massive capacitors. Again, only needs to go for a millionth of a second. They charge up these massive capacitors. The capacitors get full of energy. They rapidly release the energy to the lasers, and the energy pulses from the lasers and creates nuclear fusion at the target site. Other places where we use capacitors are great for smoothing out noise from electronic signals. What'll happen is if you suddenly get a spike in voltage, the capacitor will fill up during that spike and then slowly unload after the spike is passed. So they're great for preventing surges of electricity. The surges can build up when we have like static electricity and things. And they're also used for different circuits that have resonances to them. So again, kind of a neat device right there. It's called a capacitor. It simply stores charge. It stores energy to be used at some other time. Okay. Oh, here's another application for capacitors you probably didn't know about. Most keyboards, if they're not mechanical keyboards, my daughter just got a mechanical keyboard. It's the loudest thing I've ever heard. Most keyboards, like the keyboard on my computer right here, use small capacitors to detect when you press a button. When you press a button, okay, what you do is you depress, let me show you right here. There's this material, we call it a dielectric. It's got a positive and negatively charged molecules in it. But what happens here is your computer is constantly sending a voltage across all these capacitors, okay? So one side's positively charged and one side's negatively charged. Now, the amount of charge that little capacitor stores depends on how thick it is. The closer you make the plates, the more charge that's going to rush in onto that thing, because positive charges like to be next to negative charges. So here, if I push down on the key, okay, I compress this little dielectric, this little capacitor, and all of a sudden, by compressing it, it's kind of like the opposite of a sponge. You compress it, it actually draws more charge on it. And the computer goes, oh, that key's been compressed because I'm seeing electricity, current flowing to those capacitors. So when I press it, charge flows to that. And, you know, passing through the wires, the computer suddenly is aware, oh, key B is being pressed. Now, when I take my finger off that, the plates spread apart, and now the electricity goes the other way. So the computer sees a jump in the voltage at that particular location. Then it's going to see a dip in that voltage. When I take my finger off, I can tap on any key. They're all wired, and the computer's always sensing when charge flows toward it or when charge flows away from it. So, you know, most remote controls, those little keys, okay, they're sitting on top of these tiny little capacitors. Every time you press them, they're like little button-like material. You know, if you take the physical button off, you'd actually see like this little bubble. If you press it again, it's going to record the fact that you press that button. Okay. All right, let's talk about some other things about electricity. This is this chapter covers a lot of different ideas. So again, as we get closer to the test, I'll pretty much focus you on what is important and what is not as important. Okay. Now, we're well aware of the concept of energy. Energy is always conserved. The energy that goes into a system is equal to the energy that comes out of a system, right? If I look at how much energy I have for each piece of charge, okay, that is called voltage, okay? Or vice versa. If I look at the electric field that I place on something, how much energy each charge will be given, that's voltage. So we can think of voltage as energy per amount of charge, how much joules you get for each coulomb of charge. Okay. Now, why is this important? Why am I talking about this? Again, a volt is 1 joule per coulomb. The reason why I'm talking about this is, let me skip ahead of this. If we think about something like a battery, okay, this is a dry cell. These are typically inexpensive batteries that you can buy at just about any store. And they have a voltage of about 1.5 volt. Okay, that means every coulomb of charge will get about 1.5 joules of charge there. Now, if I put my fingers on the end of a battery, do I have any risk of being shocked? Okay, is that battery going to kill me if I put my fingers across it? Anybody? Come on, I'm asking you, is this battery safe to handle?
Yeah.
Yeah,
Okay,
it's
why?
safe.
Why is it safe to handle?
The voltage isn't high enough.
Exactly. So I got my little battery right here, and I put my fingers across it. There's not enough energy to push the charge through my fingers. Okay? So basically, at 1.5 volts, I don't have anything to worry about. Okay? I can touch both ends and not worry about the electricity going through me. All right? What about putting a knife in a wall socket? I'm sure I remember my kids trying to just putting, protectors over all the outlets. He never tried to put a knife in one of these things. But why would putting a knife in a wall socket not be the best thing for you? What's different about that in the battery?
It has more voltage by like
Does anybody know how much
10
voltage
times.
it has?
120 or 240.
Good, 120 or 240. Excellent. Somebody's an electrician. The knife conducts electricity, right? That electricity is going to go through you. You can touch the battery with a knife, but at 1.5 volts, you're not really in trouble. But the voltage coming from the wall at about 120 volts, that has enough energy to put work into the charge and send the electrons going through your body. We're electrochemical things. Actually, the ions in our battery move as well as the electrons. But as you can see here, different voltages are able to do different things. The voltage of these batteries are more than enough to send the electricity through something like this little remote here. The electronics in this remote, they don't need very much energy or very much work to get that electricity going. But the voltage which we have in the outlets of the wall, there you need a lot more energy per charge to power anything, okay? You want to plug in a fan. That motor is going to take a lot of energy to get that fan blade rotating. 240 volts are typically used for things like electric stoves. You want that electric stove to run. You're producing a tremendous amount of heat to heat up that food. You need a lot of energy to get going. So voltage tells us, basically, the charge that flows, how much energy that particular charge has. Okay, so again, batteries, small batteries, they convert chemical energy into electricity. Automotive batteries have a little more voltage at 12 volts. You're still probably not going to get a shock by touching both terminals. The problem with these batteries are if you take a conductor and touch them, the conductor is much better at allowing electricity to flow through it. You can get some pretty nasty sparks. So at 12 volts, probably not going to feel that voltage, but we're starting to get to the point where it's becoming a little bit more hazardous to handle that. Oh, by the way, talking about batteries, lithium ion batteries, by the way, work like many other batteries, allowing charge to move from one electrode to another electrode. The lithium ion batteries are probably one of the biggest technical advances that we've made in a while, because they're able to just store so much energy in such a small space. Your cell phones, these things are operating off of lithium ion batteries. My computer right now is working off a lithium ion battery. My iPad is working off of a lithium ion battery. Okay, even this little Apple pen or pencil, I keep calling it a pen. My daughters get after me about that. They all have these little lithium ion batteries. They're very efficient, can store a lot of energy in a very, very small space. And the way that they work is that when we want to charge them, we move the ions to one of the plates. In this case, we move it to what's called the anode, all right? The negative electrode. As the ions give up some of their energy, they go to the other plate, okay? It won't draw anymore, okay? So in many ways, we can think of this as similar to that concept of the capacitor where we fill up a bucket, with water. The capacitor, we fill up the capacitor with charge. Here, we're kind of filling up one side of the battery with charge, but instead of filling it with electrons, it is being filled with lithium ions. The ions like to go from one side to the other. As they go through this little separator, they're giving off their energy. When we want to recharge them, we simply send them back to the other side, and they store energy that way. But again, lithium ion batteries, as their name implies, they have little lithium atoms. Lithium is an alkali metal for you people who remember your chemistry. It's a singly charged ion, positively charged. And again, as it goes from one charge plate to another charge plate, as it moves, it actually pulls electrons on the outside to change the charge. Like when the lithium ion batteries are over here, as they move to the other plate, we're giving up positive charge. So what has to happen is the electrons have to go all the way around to the other side. And as they do that, they can do work and power different things like my phone. But again, big advancement in battery technology from the older carbon dry cells. Okay, they're nice, they're cheap to make, they store some energy. The lead acid batteries can store large amounts of energy, enough energy to start your car, but they tend to be very heavy and take up a lot of volume. So the lithium ion battery is sort of the best of both worlds. Like the carbon battery, it's relatively small, but like the lead acid battery, you can store a lot of energy in it, okay? But unlike the lead acid battery, it's a lot smaller. Okay, let's go and look at US domestic electricity. What is that electricity coming into your apartment, your dorm, your home, wherever you live? This electric service powers everything in your home. Now, what we see here is what's called a circuit breaker. We can't see it in this photograph because there's a big old wire coming in at the top right here. And there's actually three wires, to be honest with you. But that's bringing the electricity into your home. One of the hot wires is at 120 volts. The other hot wires also at 120 volts, but at a different phase. When you put the two together, you can get 240 volts. So in the United States, we have what's known as alternating current. Current goes from positive, negative, and does this every 60th of a second. And typically, most homes will be powered with two phases, not really phases, two poles at 120 volts. All right. Now, let me caution you. This box, the way that it is, this is a circuit breaker with the front taken off of it. All the metal surfaces that are exposed here, you've got to be careful. Okay. Don't try this at home, folks. Not to touch anything because of the high voltage. But coming from the power plant, it doesn't leave the power plant at 120 volts, okay? 120 volts is dangerous enough for us. Again, if we talk about both lines coming in, it's actually a total of 240 volts. But that's not the way that the power plant will send it to different locations. We can send electricity more efficiently from the power plant to our location if we send it at, let's say, half a million volts, and then use transformers to step it down, okay? So again, high tension electrical transmission lines are used to send electricities over long distances. The way our power system works is we have a grid of interconnected power plants. The power plants will have generators. They'll probably produce electricity at about 5,000 volts. But if I send that 5,000 volts across, many miles of wire, I'll lose most of the electricity. I'll lose most of the energy from that electricity as it's being sent. So what we do is we increase the voltage with step-up transformers, where in some cases it'll be boosted to about 100,000 volts. In other cases, maybe 500,000 volts. In the most extreme cases, you might even get 1,000,000 volts. Okay? Above 2 million volts, you start losing electricity to the air. But this technique of changing the voltage was very, very important. We'll talk about it in a little bit, to be able to send electricity a long distance. If you know anything about the war between, wasn't really a war, it was a dispute between Edison at General Electric and Tesla at Westinghouse, it was really about whether or not to use AC power, which Tesla wanted to use, or DC power, which Edison wanted to use. Tesla won by arguing that it was much easier to change the voltage using AC, whereas Edison needed a very complicated set of equipment to do it. Okay, believe it or not, it was up in Niagara Falls, where a new power plant was being built, that Tesla was able to convince them to put in AC generators, and this became the first basis for our power system. Okay. Now, AC and DC, what am I talking about here? All right. AC, again, stands for alternating current. This is a typical current that you get from the power company. This is the typical electricity that's coming into your home from the outside. Again, if we look at it, it oscillates back and forth between a positive and negative voltage. That's why when you look at your outlets, okay, one side's not labeled positive and one side's not labeled negative. There's actually one side which is hot, which has the alternating current coming through it, and another side which is neutral. So to label one positive and one negative doesn't make any sense. The voltage is always changing every 60th of a second. DC current is what we typically get in electronics and typically get from a battery. This voltage doesn't change, okay? Whatever it is at the beginning, as long as we don't run the battery out, that's pretty much the voltage that you're going to get, okay? So in general, batteries are very, very good at producing direct current, right? Power company produces AC. Now let's define another thing. I'm using a lot of technical terms here, and it can get a little confusing for those of you who don't have the experience with electricity. I mean, if you've done stuff with electronics or electricity, I'm probably going to bore you to death with this. When we look at electricity, we generally want to look at two basic things. How much voltage does it have, number one, and how much current does it have? We've already seen that voltage is measured in volts, and that's how much energy per unit charge. Current is how much charge is actually flowing. So when I look at current, I ask, oops, didn't want to do that. When I'm looking at the current, I'm looking at how many charged particles are flowing. How much electric charge is flowing through the wires, okay? Q, unfortunately, we use it for heat too, but here Q stands for electric charge. The more charge I have flowing, the more current I have. So it's charge that flows through a particular wire in a given amount of time. Electricity can be thought of as being very similar to the flow of water, okay? The more water you have flowing through a pipe, all right, the more current you have. Here, the more charge, if it's a metal, we have electrons that are moving, the more charge we have moving through a wire, the more current that we have. Okay, so current is really about how much flow. All right. If you want a nice analogy here, voltage would sort of be like analogous to pressure in a water pipe. All right. If you've got a lot of pressure in a water pipe, that water is going to come out with a tremendous amount of force. With current, it's sort of like, well, how much water do I have actually flowing? Okay, tiny little pipe is going to carry very much current, where a much larger pipe can carry larger amounts of water. Much larger wire tends to carry more current. Okay, once again, in metals, it's the electrons that tend to move. In other materials, it's whatever charge is free that moves. An ampere, 1 amp for short, tells me how much charge, how many coulombs I have flowing every second. Oops, I should change that to seconds. Okay, so when you hear the term amps, that's how many coulombs of charge. And electrons don't have very much charge, like 1.6 times 10 to the minus 19 coulombs. So we need a lot of electrons to even get 1 coulomb of charge. But at 1 amp, that is 1 coulomb of charge flowing every second. All right. It's not the voltage that gets you, it's the current. All right. Since human beings are electrochemical organisms, we use electricity to conduct nerve impulses through our body. It's not technically electricity, but what happens is charge will flow in and out of our nerve and our muscle cells, and this will send signals from one place to another. That's good because our central nervous system keeps us alive and keeps us doing different things. It's bad because that means that if we send an outside current through our nerves, we can override them. And if our critical organs aren't getting a signal, then bad things happen. Even worse, if we send enough electricity through our body, the energy that's contained in that electricity can heat up our tissue and actually create burns. Okay, looks like a funny photograph, funny cartoon right there. But electrical burns are extremely, extremely dangerous. So electrical current is what we're really worried about when we're handling electricity. The Van de Graaff generator, it'll produce maybe like 50,000 up to 500,000 volts, but there's so little charge that's stored in them that when you touch them, they hurt, but they're generally not dangerous. It is the current that flows through our homes that we're really concerned about, because not only does it carry a lot of charge that's moving, it also has sufficient amount of voltage to give off energy and create these burns. So again, here's a little Van de Graaff generator. Fun to make your hair stand up, not dangerous, doesn't carry very much charge. But we can actually rate the amount of charge that can flow through our body before it becomes uncomfortable, dangerous, and even deadly. Okay. Go back to my little battery right here. Pull out one of these little carbon cells. Hopefully my remote control works after this. So this is a little AAA battery. And I put my fingers across it, and I should be completing the circuit right here. All right, but I don't feel it. All right, because once again, we said the voltage was just too low. All right. With very, very little voltage, there's very little force to push the charge through, so you don't conduct very much current there. All right. In fact, we can't even feel electricity until we're up to about 1 milliamp, okay, which is 1/1000th of an amp. Okay. Again, at 1.5 volts, you're just not going to send enough electricity through your body. Probably not until you reach around 20 volts, where you start feeling a tingling sensation. And even that, it's pretty hard to feel. Okay? Well, doesn't take long. Increase the current more and more and more, and the tingling sensation becomes greater and greater. Eventually, it gets to the point where it becomes painful. At 0.005 amps or 5 milliamps, that tingling sensation starts to hurt, starts to feel like pins and needles, okay? And again, your natural instinct is to pull away from that, right? I've been shocked by hot wires from time to time, and I get the jolt, and I'm like, oh, it's annoying, and psychologically, you don't want to go near that thing again. But again, it's not usually that type of shock really doesn't do anything other than make you have a bad day. Here's where we have problems. Go up to 10 milliamps, and now not only you're stimulating the nerves in your body, you're also interfering with the nerves that are controlling your muscles. At 10 milliamps, if I send enough electricity through there, I get into a very dangerous situation where if I touch something that has a voltage to it, and I send 10 milliamps through my body, what's going to happen is I may not be able to pull my muscle away because the electricity is going to override my voluntary muscles. Okay? In fact, at 15 milliamps, I lose complete muscle control. So my chance of pulling my arm away is much, much less. If you ever come across somebody who's being actively shocked by electricity, don't touch them. Use something that's insulated to knock them away from the electricity, okay? I don't care if you hit them pretty hard, they will thank you, once they break free. Because again, if they're actively being shocked, they've lost control of their muscles and they can't let go anymore, okay? One of the worst things is that your grip at this current will actually hold tight. If you now try to grab onto that person, you may not be able to let go. All right. In the worst case scenario, as we get up to around 70 and 100 milliamps, okay, that's not even a full amp of current. That will be enough to not only disrupt your muscles, which are voluntary, it'll be able to disrupt your involuntary muscles, like your heart. Whenever I'm around electricity, the one thing I never do, well, first of all, I take my little voltmeter there to make sure that everything's dead. I make sure all the circuit breakers are turned off. But even then, I will only touch it with one arm or one hand. I'll keep my other hand in my pocket, because if I take both my hands and grab on to something that's electrically charged, the electricity will go in one hand, go through the heart muscle, and go out the other hand. So very, very important. Handling electricity, you always want to be very careful not to touch anything that you suspect has the potential to be hot. Carry electricity with both hands. And again, the electricity, how it affects you varies a little bit depending on if it's DC or it's AC. This is a point that Edison actually brought up. He always said that AC was more dangerous than DC because AC had a lower threshold for causing pain and injury. Again, for direct current, you're not going to feel it until around, 1 milliamp. By the way, folks, this is sort of an unfortunate chart here. It has men versus women here. I really don't believe that there's any difference between the two, because physiologically we're very, very similar. So it sort of says threshold of pain, that women feel the electricity to be painful lower than men. Again, I don't understand. Should change this chart. why physiologically that should be believed. But again, so it's sort of a sexist chart, if you ask me. Once again, you can see that DC has a slightly different. Hey, why did it do that? DC has a slightly different threshold of feeling than AC. Usually at AC, you feel it earlier. It's more painful. You lose control to release. And also, well, okay, heart fibrillation after 3 seconds at a half an amp. So again, it all depends on how you make contact with it. But the one thing we want to make sure of is that you do not combine live electricity with water. And we've actually come up with some really nice devices to prevent injury around damp locations, okay? Again, if you touch a positively charged component with one hand and a negative charged component with another component, the electricity will pass directly through your heart. If you touch with your hands and you're in a wet location, your feet are in wet location, it can pass through your body. All right, let's skip through some of this. There's a quick law. We don't have very much time, so I'm not going to put all of this on the test. You know, whatever I covered today, I'll put on the test. But there's an important law which was developed by Charles Ohm, which related the voltage in a circuit to the current that flows times something called the resistance, okay? Now, the resistance, which is measured in ohms, oops, wrong color, measured in ohms. We use an omega symbol for the symbol of ohms, tells you how much voltage you need to get a particular current, all right? Now, the lower the resistance, the easier the electricity flows through something. The higher the resistance, the more voltage we need to get the same amount of current. Again, ohms represents how much resistance it has to that flow, okay? Look at this equation. We can rewrite it as I equals V over R. And again, the resistance is in the denominator right here. If you want to know how much current we can get through a wire, depends on the voltage of the wire, but also how much resistance that wire has. So again, that's called Ohm's law. We write it as V equals IR. If you take an electronics course, it's such an important equation, okay? But again, relates voltage to current. And of course, the constant that relates it to is resistance. Let's do a little calculation here to demonstrate Ohm's law. V equals IR. What is the voltage across a 680 ohm resistor? Once again, there's that symbol for resistance. 680 ohms means it takes 680 volts for every amp of current that I'm going to get. All right. So what is the voltage across a 680 ohm resistor if the current is 26.5 milliamps? Okay. Well, first of all, we got to convert milliamps into amps. Mill is 1/1000. So if I take my milliamps, 26.5 milliamps, and divide by 1,000, I get 0.0265 amps. Okay. Now we're going to put in the resistance, 680. Okay. So for this I right here, at 680 ohms, I need 18 volts to get that much current through there. All right. So that shows you how Ohm's law works. Okay. The lower the resistance, the less voltage you need to get the same current. see if I can do another example right here. Here, I have a light bulb hooked into a wall outlet. Much of the time that when we talk about house current, it's typically referenced at 115 volts all the way up to 120 volts. So, don't be surprised if you actually measure the voltage in an outlet and you see something that's somewhere between 115 and 120. Okay. Usually, if the voltage is under 115, you've got some type of problem. You're probably drawing too much current. If it's over 120, that's unusual. Usually means that there's a problem with the electricity that's servicing your house. In any case, so here I have 115 volts of electricity coming from the outlet. I hook an ammeter up to the wires to see how much current is flowing through it. An ammeter measures how many amps are flowing through a wire. So I connect one side of the ammeter to one wire and the other wire going back to the outlet. What is the resistance of this light bulb? Well, the resistance is equal to how much voltage I have in, put 115 volts in, how much current I have out, 0.87. So 115 divided by 0.87, 115 divided by 0.87 gives me 132 ohms for that particular light. Okay, so this is interesting. Smaller appliances tend to have more resistance. Okay, smaller appliances need less current to operate them, so their internal resistance is going to be greater. Bigger appliances, like, I don't know, an electric oven, is going to have a really low resistance. So when I plug it in, I get a very high current out of it. All right. Okay, we'll go over the electric power equation. I don't think I had enough time to do this, but we'll do this.
Professor,
The
I
equation.
have a quick question. I'm sorry to cut you
Sure.
off.
No, go ahead.
So a
Ask
socket,
questions. Okay.
a socket and a outlet, it's the same thing, right? That's basically in the wall where we plug in the wire.
Oh, am I using those terms interchangeably? Okay.
Oh, no, I was confused about
Okay.
it. That's why I wanted
Sorry.
to ask you.
Sorry. Good question. So typically we say a wall outlet. Okay. An outlet, a power receptacle is going to be this thing in the wall that we can physically plug a plug into. Normally, when we say a socket, we're talking about, and I apologize if I've been using them interchangeably, something we can screw a light bulb into, like down right here. Sockets you typically screw, some type of light into, and outlets we put a physical plug into.
All right, got it. Thank you
Sorry,
so much.
Sorry about
No
that.
problem. It's okay.
I didn't mean to confuse that. I do so much electricity that I'm just like, oh, everybody knows all these terms, and I just throw them around, and I'm like, maybe I should be a little more descriptive about what I'm talking about and explain the context of these things rather than just assuming everybody's a licensed electrician. One interesting
Wait, are
thing.
you?
No.
I was about to say, you make
I'm just a
hella
physicist.
bank because they make good money.
They do. And you know what? An aside, one of the big problems that I have up around where I live is, to get an electrician or to get a plumber out, it's not only difficult because there's so few of them. Yeah, they make great money. I'd like to make one. They work hard. Don't get me wrong. Electricians, plumbers, it's very physically intensive sometimes, and they work for every penny that they make. But yeah, electricians who are licensed, especially up in New York, because it's tough to get your electrician. It's more difficult to get your electrician's license in a state like New York or a state like New Jersey. I know one of my friends is a licensed electrician. I can't even get him out. He has people working under him, and he's gotten to the point where he's got so many jobs going. He just has to inspect the stuff at the end. As a licensed electrician, he's barely doing any of the work. He's basically a businessman running his different workers here and there. They are not
That's the life.
licensed.
That's the life. That's the life I'm talking.
Well,
You
the
just sit
problem,
back and you let your workers.
well, the problem is owning a small business. You got all the headaches with it. So yeah, he's a licensed electrician, and he has to go to the different sites and he has to inspect different things. But he's basically running the business himself. He's got to worry about payroll. He's got to worry about benefits. He's got to pay workers' comp, because obviously they're operating with some somewhat dangerous things. Again, does very, very well, but he's always working, and always going to different sites, pretty much like a GC general contractor would be on a construction site. He's sort of managing the different people that work for him. It's good for him because he's middle-aged, and as you get older, you don't want to do as much physical labor. But again, with any business, especially if you're the one running the business, everything falls on you. So that's what he's up against. But yeah, I mean, I'm a college professor. I should be encouraging you to enhance your education. But if you want a good career, yeah, any of these trades, we've got a shortage in this country. Everybody's doing very, very well there. And the funny thing is, he went to school to be an electrical engineer, and got his electrical engineering degree. Just started a side business doing this and did very well for himself. He never needed to go to school for electrical engineering, so paying back that loan. Oh well. In any case, I digress. Power equals current times voltage. If you look at the power that some device uses, you can usually look on the back of different different electrical devices. I don't have anything in this room that I can pull, but they'll tell you, first of all, oh, I need a different color. Come on, right. How much current they'll pull. So they'll say like, I don't know, I'll make up something here. Let's say 0.20 amps, okay? Or 200 milliamps is the equivalent right there. If I plug that appliance into the wall, and I know that it uses 200 milliamps, I can calculate the power because I can calculate the power because I know the current. I got to keep everything in SI units. Amps are the SI units for current. So at 0.2 amps, if I plug that into a wall outlet at 120 volts, 0.2 times 120, okay, is going to give me 20. I could actually, you had a brain fart there. I couldn't do that in my head. 24 watts of power it's going to use, okay? So larger appliances tend to draw more current for the same voltage. So for instance, let's say I have a 1200 watt toaster oven, 1200 watt microwave, 1200 watt microwave, okay? That's going to draw a much bigger current, and maybe like 10 amps, okay? So when I calculate the power, my 1200 watt microwave at 10 amps times 120 volts 10 times 120, there's 1200 watts. All right. So that's the other important equation that we have with electricity. 100-watt light bulb. We can calculate the current based on the power. You can write it as current is equal to power over voltage. I'm just turning that equation around. Okay. And I see a 100-watt light bulb. Divide by the voltage, how much power per volt will tell me that I get 0.83 amps. Skip that equation. It's getting more complicated. It's 11 o'clock. I need to go anyway. So folks, that's as far as we're going with this particular chapter. Okay. You're welcome to look through the rest of it. It talks about alternating current. There is some stuff about wiring. Let me just say this. Don't do your own wiring unless you know what you're doing. You know, it's dangerous if something goes wrong. You can get a fire. But you know, it is interesting to look through the different aspects of how the current comes into your home, how breakers work, how arc fault circuits can protect you from getting fires. And one of the most important devices is what's called a ground fault circuit interrupter, GFCI. These are things that you want to have in wet locations. You never want to operate somewhere where it's wet. Maybe it's outside, maybe it's in the kitchen, maybe it's in the bathroom, and not have one of these outlets connected to your circuit. What this does is, if electricity comes out of this outlet and not all of it makes it back in, that's telling the circuit that some of the electricity is escaping someplace. Now, if it's escaping from you, that's not a good thing. Okay? If you plug something in and it makes contact with you and some of the electricity starts going through your body, in 1/40th of a second, that GFCI circuit will shut down and not let more than 1/10 of an amp through your body. Okay, so safety first. These GFCI are great protection to keep you from getting electrocuted. Okay, folks, I got to run. Thank you so much.
Thank you, Professor. Have a good